Hello, everyone. So this is Jie Ying from Google. I'm going to talk about PJRT, simplifying ML hardware and framework integration. In last Open LAX Summit, we had introduced PGRT and open sourced it as part of the OpenXLA ecosystem. We developed it in partnership with many of you to simplify the growing complexity of ML workload execution across hardware and frameworks. In conjunction with Stable HL, this addresses ML infrastructure fragmentations across frameworks, compilers, and runtimes, enhancing the industry's ability to productionize ML-driven advancements with velocity and at scale. Let me give a quick overview of what is PGRT and what does it give you. PGRT provides a hardware and framework-independent interface for compiler and runtimes. It simplifies the integration of a hardware to the infrastructure, accelerating the framework coverage of different hardwares and also the hardware targetability for workload executions. And therefore, if you are developing an ML hardware accelerator, compiler, or runtime, targeting any hardware, or converging silo tool trains to solve infrastructure fragmentations, PGRT can minimize bespoke hardware and framework integration and providing greater coverage and improving time to market at lower development cost. As a foundation pillar of the OpenXLA project, PGRT is well integrated with projects within the OpenXLA project, such as Stable HLO and the OpenXLA compiler. PGRT is the primary interface of TensorFlow and JAX and fully supported for PyTorch through PyTorch XLA. It is well integrated with the OpenXLA compiler to execute the workloads on TPU, GPU, and CPU. It is also the default runtime execution path for most of Google's internal production workloads. Meanwhile, PGRT is not tied to a specific compiler. With framework integration through Stable HLO, PGRT can be used outside of the OpenXLA ecosystem, including other proprietary compilers. And the open source availability and toolchain independent architecture allows it to be leveraged by any hardware, framework, or compiler with extensibilities of unique features. Let's go into a little bit more details about what a plugin authors and frameworks need to do with PGRT. For plugin authors, they need to implement the following features: compiling a program to executable, execute an executable with input arguments and generate outputs, memory management such as host to device, device to host, device to device transfers, as well as buffer management. You also need to provide topology information such as platform info, how many accelerators are there, etc. And lastly, you need to register the plugin to the framework. And these implementations will be opaque to the framework. And from the framework's perspective, you need to discover and load one or multiple PGRT plugins, provide forward compatibility and version checking for features, and calling device agnostic PGRT APIs. One natural question is that how is the current adoption? So beyond Google, PGRT has been adopted by industry partners through close collaborations. For example, Intel is leveraging PGRT in Intel extension for TensorFlow to provide the Intel GPU backend for TensorFlow, JAX, and PyTorch. There was a related presentation in previous OpenXLA Summit, and there's also a collaborative blog post with more recent updates. And they have an example of executing a JAX program on Intel GPU that demonstrates that how this greatly simplifies the framework and hardware integrations. And today, we are also going to talk about a few new PGRT plugins targeting other hardwares. So this is the overview of the remaining of this presentation. First, we will go over the new plugins, and then I will go over some highlights of PGRT API updates. Let's first take a look at the PGRT plugins for existing backends. So we have extracted the NVIDIA GPU CUDA implementation in JAX and changed it into a PGRT plugin. This is a dogfooding that PGRT works. And the NVIDIA GPU backend is quite complex. So by turning it into a plugin, we hope to get ahead of any issues that you may encounter when implementing your own plugins. Some features like DLPack were recently added to support the GPU use case, as well as we also implemented registering custom calls through the PGRT extensions. And with this change, no custom C++ code in JAX is needed to support NVIDIA plugin, and we can ship CUDA support on PyBy, and which is simpler for the users. I also want to mention that the Cloud TPU backend in JAX is already a PGRT plugin. And this is actually our first PGRT plugin and now getting mature. With both the NVIDIA GPU CUDA plugin and Cloud TPU plugin, it is demonstrated that JAX can support multiple plugins, and the PGRT API can cover the use case of different hardwares. We're also excited to talk about the collaboration with Apple. Apple has released a PGRT plugin to support running JAX on Metal. As you can see on this slide, thanks to the PGRT plugin interface, adding Metal support to JAX is just as simple as a pip install. Apple Metal plugin's focus has been on JAX, but this will clear the way for TensorFlow and PyTorch XLA. We think this is a really great example of the value that the plugin interface could bring to ML users. These are the benchmark numbers presented by Apple at WWDC earlier this year, and adding Metal support to JAX enable users to get more out of their hardware and speed up their workloads, allowing them to iterate and experiment faster. And JAX composable transforms are also usable seamlessly with the Apple plugin. So that concludes the new plugin updates, and I will quickly go over some highlights of PGRT API updates. The first update is the ABI compatibility. So PGRT API has a major version and a minor version. If the framework is newer than the plugin, the framework will provide a N-week forwards compatibility window and for minor version updates. As a start, the N-week will be 6 weeks. And then for the major version update, it will be a coordinated update, and framework will not support plugins with an older major version. If the plugin is newer than the framework, plugins define their own backward compatibility policy. We also added a concept of memory space to PJRT. Memory space is where a buffer is attached to, and memory spaces will be attached to the PGRT devices. Some example memory space and like are host memory space, HBM, and R1 cache. And JAX has an API, jax.deviceput is already support, allow the user to put a jax.array on a specific memory space, which will empower the user to better utilize the memory for their workflow. This feature is only supported on TPU right now. And for plugins that do not implement memory space, you will have the default behavior, which is one memory space per device. Another update I want to mention is the multi-node support. So PGRT client is per node, and the plugin in general may need some way to communicate between nodes. The framework can pass in a key value store callbacks to the plugin, and the plugin can use them to bootstrap multi-node initializations and other coordination needs. For example, in the NVIDIA GPU CUDA plugin, JAX starts a distributed service in the JAX framework and then passing the callbacks, and the CUDA plugin will use these callbacks to generate a global device topology that assembling all the information from different nodes, and then also use it for generating for Nico IDs. And the last update I want to mention is DLPAC support. A few C API was added to support DLPAC. Create view of device buffer, which supports receiving buffers from DLPAC, and exporting buffers to DLPAC requires a few C APIs, increase the external reference count, decrease external reference count, and get an opaque device memory pointer. So what's next? There are a few items in our mind. The first is to support optional features, that is indicating whether API is required or optional, so that the plugin authors can implement the minimum set of APIs needed for their workflow. And the second is to support experimental features that the framework does not need to maintain compatibility. The framework will support either the experimental feature is not implemented, but it will not support like an older version of implemented experimental features. And the last item is about JAX Python APIs related to plugins. We have a private API to register to do the automatic discovery and plugin selection, and we'll make it public. We also need to think about how to ship plugin-specific Python APIs in addition to the PGRT implementations. And these similar APIs can be implemented by other frameworks. So if you want to learn more about PGRT, please check out the resources here, join our announcement mail list, and also we will have a breakout session later today. Thank you.
Excellent, thank you. We're gonna keep it to one question before we move on to AWS.
Thanks, Chairman, for the talk. One quick question: is D2D data transfer works for a device data transfer works for devices between devices in different hosts, or it only works between the devices on the same host?
It will be in the same notes.
Same host. Okay, thank you.